Hello and welcome back. Today we are discussing Chapter 2. We're moving on to a new chapter, Section 2.1, which is the derivative, kind of the pivotal concept for our whole quarter, actually. We're going to take a look at some of the preliminary stuff to get there, and that's our first learning objective. Examine slopes of tangent lines and rates of change. So before we get to the derivative, which is its own special kind of rate of change, we'll talk about one that you've probably encountered before. Ideally, you ran into the average rate of change in a college algebra course. But just to make sure, average rate of change of some function, we need to have an interval over which to work. So we're going to call that a to b just for convenience. And then here's our expression for that. So if we look at this kind of carefully, you might notice some similarity to something we've already done. F of b is just an output, so maybe I could call that a y. F of a is some other output, so to keep them separate, I could call this one kind of y and this another kind of y. I'm being sort of sneaky about this. I'm choosing these on purpose. And then on bottom, b and a are x values of the interval that we're operating our inputs on. So these are each x's. And the b goes along with the input to this first expression on top. So we could call that, say, x2 to match up with the y's. And then a goes along with this input. So f of a corresponds to y sub 1. And then, if you haven't noticed already, this is basically just the slope formula. It looks like y2 minus y1 over x2 minus x1. And that's what this final note said, that this really is just the slope of a function in some sense. I put slope in quotation marks because when we talk about a slope, it should be a constant rate of change. And for functions other than lines, it's not clear that we would have a constant rate of change. In fact, lines are very special that way. All other functions have varying rates of change. But this is our average rate of change, and again, it's just the slope formula, but fancied up with some function notation to illustrate that we could be doing this for things other than lines. So a quick example just to get us in there. We've got 3 minus 2x is an expression defining our function, and we're in charge of finding the average rate of change between -1 and 2. So just to follow through the pieces of work that we're up against here, there's our inputs, 2 and -1. Those also appear on bottom. Here are the x values that got us there. So this is essentially 2 is b in this case, and -1 is a, using the same structure that we were given in the definition a moment ago. And then in order, really the only computation is to figure out what this actually looks like, and in order to do that we refer back to our actual function. So we've got an equation that defines the function at any given value of x, and so on top we just plug in 2 and we plug in 1 respectively. So these are just our function back again, but with different inputs. So now we've got entirely numbers. 3 minus 4 is -1. 3, that's actually plus 2, gets us to 5. And then we have to be a little bit careful about this whole subtraction situation, but we are supposed to subtract these two terms independently. So we've got -1 and then -5 on top. We've got 2 plus 1 on bottom. So we end up with -6 over 3 or -2. And the function that we picked was kind of special. It is linear. It does look like y equals mx plus b. And so it shouldn't be any surprise, actually, that our answer that we get for average rate of change would be the exact same thing as the slope of the function. So if we go back up here, there's our m, and that agrees with the average rate of change. And so this is just saying that, in particular, between the points -1 and 2, the slope is -2. But that should be the same no matter which 2 points we picked for this particular function, for any linear function. This average rate of change is going to be the same. We'll try one additional example. So the cost to produce k quarts of kettle corn is given by some production function. So I guess to lend some legitimacy to this, the thing I'm thinking about is about $50 worth of upfront costs, fixed costs. Maybe this is buying a machine to cook the kettle corn and so on, or rent it. And then this is the portion of the variable cost that seems directly related to how much we produce. So this is maybe 50 cents per quart that it costs us to produce the corn. Maybe that's purchasing the corn itself, labor costs associated with cooking it. And then this quadratic term you could maybe think of as an economy of scale somehow. The more corn we make, we get a little bit of relief in how much it costs for us to produce. So not a whole lot. This negative 0.1 doesn't make this change a great deal until we're producing a lot of corn. But at any rate, there's an attempt to describe why this might be our cost function. So our actual task here is average rate of change in cost when we move from 10 to 20 quarts. So notice that K was in quarts of kettle corn, so we don't have to do any modifications to this. This is just K equals 10 and K equals 20. Okay, so there's that statement. Average rate of change looks like our definition. So it was f of b, but our actual function name is c, so we're going to use capital C for cost. We're evaluating it at the end and then subtracting cost at the beginning. It should not matter if you did C of 10 minus C of 20, as long as on bottom you also reverse the order of this subtraction. So it would be 10 minus 20. Okay, but just like with our quick little example in the line, the only real computation here is to figure out what C of 20 and C of 10 look like. So C of 20, first off, we go back to our formula, replace all of the K's with 20's. There were two spots where we saw K. And then either do some mental math here, it's actually not too bad, or have a calculator, Wolfram Alpha, etc. help us out. But we come up with a cost of $56. And then this is the cost to produce 10. So essentially on top we're figuring out how much more does it cost to produce 20 units than it costs to produce 10 units. That's this difference. So it costs 56 to produce 20, it costs 54 to produce 10 quarts. And then we're supposed to put it all together by taking the difference on top, 56 minus 54, and then the difference in inputs on bottom. So this is not just how much it changed, but how much it changed relative to the growth in production. Okay, so cost divided by quarts, I guess, gives us 0.2. And we were explicitly told to give units, so we want to make sure we do that. Here we've got, just in general, units on this kind of average are units of the output, just stuff on top. These fellas are units of our output, and that's a cost, so dollars would be our initial unit. And then the units on bottom, which are the units on our input, magenta, yes, that'll get your attention. Input there, and then quarts are the units on that, so then those are our units that go in the denominator. So our unit on the average overall is our number, 0.2, and then the units are dollars divided by quarts, so dollars per quart. We'll try one more abstract one. So we have several jobs on this one, and we've got a relatively nice function. We're supposed to find average rate of change on the interval 1 to 2, on the interval 1 to 1.1, and then this is not well defined, at least not yet, so it gets quotes around it. What does it mean to find an average rate of change at a point? So that'll require a little investigation. But the first two are pretty quick. So compute the average rate of change of x squared plus 1 on this interval. So we're going to take our average rate of change formula again, dump in 2, plug in 1, and then 2 squared plus 1, that's f of 2. Get magenta back again. There's our f of 2. And then plugging in 1 to our function. And finally simplifying that, I think we get, let's see, that's 5 minus 2 is 3. So 3 over 1 is 3. There's our average rate of change. Great. So then we move to a slightly smaller interval, just 1 to 1.1 now. And here the motivation is we started off with the broad interval from going from 1 to 2. Now we're narrowing it down, and we're not going as far away from 1. We're just going 0.1 units up from 1 to 1.1, and then computing that average rate of change again. And so what we get, we plug in 1.1 to our function, plug in 1. Here's all of the interesting stuff in the numerator. This might require a calculator, but 1.1 squared is 1.21. So up to 2.21 minus 2, and all that with division gives us 2.1 in the end. And then finally, we have to figure out what at x equals 1 means. And the challenge is that our formula for average rate of change involves two distinct points. So we can't really just plug in one for both of those points. We would get something that looks like 0 over 0. So instead, let's just pretend we'll go a little bit either up or down from 1, and we'll call that distance h. So this, I know this is going to take a moment to absorb, but this right here, that input, is supposed to represent 1 plus or minus a little bit, because h could be a negative thing too. But I'm supposed to picture in my mind that h is something small, like 0.001 or negative 0.00111 or something like that. So it's a tiny distance away from 1, because what we're really trying to explore is what would happen if we crept closer and closer to x equals 1. And this is basically the first moment where we start to see any reason why we might have discussed limits the last couple of sections. Because when we talk about h creeping closer and closer to some number, whenever we say approaches, then we're probably referring to a limit of some sort. So at any rate, what's in front of us right now is this computation. We're supposed to take 1 plus h and dump that into our original function. So we'd have 1 plus h all squared. Parentheses really are important here. Just to keep track of what we've got going on, we should note that this all turns into everything in parentheses here. And the most complicated portion of that is the 1 plus h squared. So there's 1 plus h squared, and that's this expanded piece. Try not to fall into that trap where you say that this expression, 1 plus h all squared, is 1 squared plus h squared. We really do have to take 1 plus h and multiply it by itself to get this solution. So anyway, so the stuff in green expands if you FOIL it, or distribute is probably a better term. And then beyond that, we've got some stuff that cancels in the top. We've got 1 plus 1, but then minus 2. So all those are out of the mix. And then if I can throw one more color into this mess, we've got 2h plus h squared. So, and then an h on bottom. So actually we can cancel out a factor of h from each of these. So with all those hash marks and underlines and circles and whatnot, all that's left is 2 and h, because everything else got divided out. And considering where we started, that's a pretty impressive simplification. That's actually pretty tidy. So now we have to deal with this at situation. So what we're trying to look at is the trend as h gets closer and closer to 0, because h was our distance away from 1, and we'd really like to be at 1. We'd like to be at a distance of 0, but we recognize that's going to cause this thing to be undefined. But here's the great thing. All that algebra that we just did results in something that is not undefined. It is defined when h is equal to 0. If we started with this expression, this is taking our average rate of change and tacking on this limit expression. If we take all of this and actually tried to plug in h equals 0, we would be in trouble. Because we'd have f of 1 minus f of 1, that's 0. And we'd have 1 minus 1, which is also 0. 0 over 0, as we have seen in the past, not a very useful expression. I don't really know what that is. But if you take all the simplification that we just did, this whole big chunk of stuff, all of our work turned it into just plain old h plus 2. You can look back at the couple of slides that we just did for all of that process. So here's the great thing. We've got this theorem that says, look, as long as this expression is a polynomial, or at worst, a rational function, you're dividing two polynomials, then, and this limit is defined at this spot, then you should just plug it in. The limit is the same thing as this expression in magenta here, evaluated at 0. So really we can let h be 0, it's out of the mix, and all that's left is 2. Which is delightful, because that actually tells us the slope at x equals 2. And so here's a visual to go along with all of this stuff that we just put together. F of x equals x plus 1, it's the same blue graph in either case. The curve is the same in each of these two pictures. The secant line is actually what corresponds to the first thing we did. We figured out the slope between x equals 1 and x equals 2 on this graph. So if you draw a line connecting those 2 points, you get the secant line on this interval. And then even more exciting, we have a line that is at, in some sense, at x equals 1. So this is the slope of this curve, and you can see it basically just bounces right off the edge of it. That's what this tangent line is referring to. If you have a tangent in some conversation, you all start at the same place, but then somebody sort of shoots off in a different direction. So this tangent line has the slope equal to that average rate of change we just finished computing, the slope, quote, at x equals 1. And then it has to touch this point on the graph as well. And what we'll see is that the slope of this tangent line is this very important definition that we've got that we'll define in this section in the next video, and it will carry through throughout the term. Thanks for bearing with this slightly longer than usual video. Talk to you in the next one.